In this video, we'll be talking about particle motion and parametrics with particle motion. Okay, for our first question, we were looking at a squirrel that starts at a building. We have time as 0, travels along a straight horizontal wire connected to building B. And so from time 0 to 18, the squirrel's velocity is modeled by the piecewise linear function defined by the graph above. So it's important that it's telling us that this is piecewise linear. So we do have slopes involved. And part A, at what times in the interval from 0 to 18, if any, does the squirrel change directions, and give a good reason for this. So what we'll be looking for is where the squirrel's velocity is changing signs. And that velocity would be changing signs here and here. So we're going to say that the squirrel changes direction at time t equals 9 and t equals 15 because, and thinking about this, this is going to be where we go from above to below or from below to above. So that's going to be because V at t has a sign change. Right, and on the free response, this would have been worth 2 points. Okay, in this free response, we are looking for some time t where the the squirrel is farthest away from building A, and at what time. So we've got a couple of things that we need to look for here, and we will set up a chart. So we have a time frame, and then we also will have our position at that time. So our time values that we need to choose, again, here it's the farthest from the building. So we need to think about this as an absolute max during that time. So for absolute max, it's over the time frame from 0 to 18. So those are numbers we need to consider. And also where the particle, or squirrel in this case, is changing directions. So we have a total of 4 values that we need to investigate. So we have 0, and then we have time at 9, we have at 15, and then finally at 18. And since we have a velocity graph, to find the position, we're going to have to find the bounded area. So at, of course, 0, then we have 0. So we're still there at 0, 0 there. Now over here at 9, then that's going to change a little bit, because now at 9 we need to consider this whole region here. That's going to be the area that we need to find, and so that area inside there is going to be the area of a trapezoid, so it's 1/2 the height, and the height is 20, times the sum of the bases. So this base up here is going to be 5, and then the base at the bottom is going to be 9. And so that's going to be 10 times 5 plus 9, 14. So that's going to give me 140. All right, and so now let's look at the next region that we have, and that next region over is going to be inside here. And so we need to calculate that. Now keep in mind that we've already traveled 140. And so now when we come back over here, again, we have 1/2 the height, which is 10, times the sum of the bases. So I've got 9 to 15. So 9 all the way out to 15. We're going to have 6 plus, and then from 10 to 14, that's 4. And so notice here we're going to end up with 10 times 10, half of that. So at 50, but now we are below, and so this portion here is going to be 140, the portion that's above, all the way over, so minus 50, and so that region is going to be 90. And then finally the last portion here, this is going to be another trapezoid. Great trapezoid problems here. And so what we need to do with this one, we do need to drop that height, and then we need to find this bounded area here. And if we do that, then we again have 1/2 the height, which is going to be 10, times the sum of the bases, so 2 plus, and we're going from 15 to 18, so that's going to be a total of 5. And so that's going to give me 25. And so again, we already have 90 here. So 90 plus 25 more, that's going to give us 115. So now we have enough information to answer this, and it would make sense that at time t equals 9, the squirrel is the farthest from building A. And then we need to also say that the greatest distance, the distance is, and it was 140. Right, and then part C wants us to find the total distance. Now for total distance, that is going to be an absolute value. Do keep in mind total distance, a good little review here. That total distance is going to be the integral, especially from 0 to 18 here, is from 0 to 18, an absolute value of the velocity. And so that's really talking about where we would flip this over here and have this graph going on. Of course, do a better job of drawing than I do. And so that chart that we just filled in is going to be pretty handy here, because we're going to go back and say, well, I know the first part that we had was 140, and then plus, and then we had that portion that was negative 50, but now we're going to flip it over, so it's going to be positive 50, and then the last portion was 25, so that total distance is 215. In part D, they want us to write an expression for the squirrel's acceleration, velocity, and distance from building A that are valid for 7 to 10. All right, so from 7 to 10, notice that that's talking about this region here and this region here. So from 7 to 10 is going to be talking about this portion. All right, so let's see if we can't set that up from 7 to 10. For the first portion here, we could talk about acceleration. So A at t is going to be equal to, and so from 7 to 10, that's going to be the slope. This is the graph of the velocity. So I need to talk about the slope of this line segment here, and that's going to be this segment here. And we do have 2 points here. So to set that up, we're going to say 20 minus negative 10 over 7 minus 10. And so that's going to give us negative 10 for the acceleration. Now for the velocity here, let's see, what do we need for that? Just an expression. So we need the equation of this line segment. And so for our velocity, v at t, sorry, we need the equation of that line. So we can pick a point on it. It's not going to matter which one. I'll just pick that point up there. So we're going to say y minus y1 equals our slope, which we just found, times, and then x minus x1, so x minus 7. And so to finish this out, solve for y, we're going to add 20 over, and you can leave it like this. You've got negative 10 times x minus 7, and then plus 20. And then we need to talk about our position, which means that we need to integrate our velocity function that we just found. So, and I'm running out of room, I'm going to move this up here to the top. So over that, we do need to do some kind of integration here. And we know that our position at 7 is, let's see, we can go find that number crunch in here. It's going to be 120. So our position is going to be our position at 7. And then, and again, I'm using 7 because here we're looking from 7 to 10. And so here we can go through and number crunch. Okay, so we need to go ahead and finish writing out that velocity function and simplifying that. And if we do so, we're going to have y equals, and that's going to be negative 10x plus 70 plus 20, so plus 90. Now, what we're going to have to do, though, because we need our position function, is we're going to have to integrate this. And so we know here at 7, we've got some values there. I know the whole thing for this, going through the whole part from 0 to 9, we found that to be 140. And then we need to take off this portion here, 1/2 base times height. And if I take off that portion, that's going to give me 120 for that other portion. All right, so now I think we're ready to integrate. So if I integrate this, then that's going to give me my position. And so if I integrate negative 10x, that's going to give me negative 5x squared plus 90x plus c. Now, I know, again, at 7, I have 120 as my position. So I'm going to plug in 120 equals negative 5 times 7 squared plus 90 times 7 through 630 plus c. And so this problem is not ever going to end, I don't think. So that's 120 equals negative 49 times 5, 245 plus 630 plus c. And so when you number crunch that mess, then c is going to end up being negative 265. So now I have my position function, which I'm completely out of room for. So my position function, x at t, is going to be negative 5x squared plus 90x minus 265. Okay, in our next problem, we have this awesome student, Karen, who is riding her bicycle to school. And so in part A, we need to find the acceleration of Karen's bicycle at time 7.5. And at time 7.5, notice it's going to be sitting somewhere in here. This is a linear piecewise function. So to find this acceleration, at 7.5, we can really just look at the slope of that segment between 7 and 8. And so that's going to give us 0.2 minus 0.3 over 1, and that's going to give us negative 0.1, and I believe this was miles per minute squared. All right, so now let's look at the next part. Using correct units, we need to explain the meaning of our integral from 0 to 12 of the absolute value of v at t, and we also need to find that value. All right, so starting off, we do need to explain that if we're going to look at the integral from 0 to 12, absolute value of v at t dt is the total distance Karen traveled over time. Oh, I need to tell distance in miles. I need my units. It says correct units. Total distance in miles Karen traveled over time, t equals 0 to t equals 12 minutes. All right, now let's do some number crunching here, and that's where this gets to be a little aggravating of a problem because there's so many small places here. If we've got to find this distance, then we're actually finding these bounded regions. So we've got to go through and find each little individual bounded region here. And I just divided this up into several little parts, and also this portion over here. And I'm going to write down the values that I got for each small portion here. So for the first part, whenever I went through, I integrated from, it was from 0 to... went from 0 to 2. That was the first place that I thought might be a good break. Now, you're welcome to do other areas, but that's just where I got to, and that was 0.2. Then I went from 2 to 4. Oops, I forgot my dt. That's all right. I'll pick it up there. And that, again, was 0.2. And then I did... because there's a flattened out area there, so I skipped on over and did from 5 to 6. And again, that's just the first thing that I saw to do. In that bounded region, I got 0.15. Then I did 6 to 7. 6 to 7, I got 0.3. And then I did 7 to 8. 8 of that distance, and that was 0.25. And then we finally need to find the bounded region from 8 to 12 and finish this mess out. And if you do that, you should end up with 0.7. So the sum of all of these is going to be from 0 to 12. V at t dt should be about 1.8 miles. All right, so in part C, it says shortly after leaving home, Karen realizes she left her calculus homework at home. Well, how sweet. She turns around and goes and gets it. And at what time do we feel like she turned around? And we're going to say here at time t equals 2. So we're going to say that Karen turns around at time t equals 2 because this is where velocity has a sign change. All right. Okay, so now we're talking about Larry, living the life of Larry. So we want to know who lives closer. And so for this one, it is a calculator problem, so that is good. And again, we need to find that total distance. So what we're going to do is integrate Larry's equation. And so if we do that, then for here, and again, calculator problem, I'm going to integrate from 0 to 12. And notice here, this is really talking more about displacement. And so we are just going to integrate W at T dt here for Larry. And that, after you put it in your calculators, you should get about 1.6. And then for Karen, this is where we're going to go back and drop off all of those absolute values, the positive parts. And if we do that, then we're going to get 1.4. And so notice that Karen lives closer. Okay, for our next problem, we have a particle that moves along the x-axis so that the velocity at time t from 0 to 6 is given by a differentiable function v whose graph is shown above. The velocity at 0 is 0 at times 0, 3, and 5. And the graph has horizontal tangents at 1 and 4. The areas bounded on V over those intervals would be 8, 3, and 2 respectively. And at time 0, x is negative 2. So they've given us quite a bit. So for the time between 0 and 6, find both the time and the position of the particle would be farthest to the left, and we need to justify our answer. All right, so I know for sure from 0 to 3, we're bounded below the axis, and that is 8. Above, from 3 to 5, we have 3. And then here from 5 to 6, we have this little region here that is 2. All right, so farthest to the left, it looks like it's probably at 3, but we need to be able to justify that. So that's where having the information that at 0 the particle is at negative 2 definitely is going to play a big part. So we have a question about where this might happen at, and so farthest to the left, I would think maybe we need to see, well, what's going on, or what is the position here at 3? And so the position at 3, well, we know at time 0, the particle is at negative 2. So I'm going to say negative 2 plus, and then I'm going to integrate from 0 to 3 of our function v at t dt. And so that's going to give us negative 2 minus 8. So there we're at negative 10. And then we go back to positive, and then we're going to go back to negative at 6. So it might be a good idea to find the position at 6 just so that you're justifying your answer. So here we're going to go all the way out to 6. And again, we know at 0 we're at negative 2 plus, and now I'm going to integrate from 0 to 6 of v at t dt. And so we have our negative 2. We also have, let's see, as we're going through here, we have negative 8. But then we're going to go back to a positive 3 and then a negative 2. And so, wow, this is close. We're going to have negative 10, and then we're going to have negative 7 minus 2, negative 9. So as close as that is, the particle is farthest to the left at time 3. And so let's go ahead and make that statement. The particle is farthest left at time t equals 3. Okay, on part B, for how many times of t between 0 and 6 is the particle at -8? So the first thing we need to consider is whether or not what we have is continuous. So I'm going to come back up here and look, and notice it says given by differential function v. So the first statement I'm going to make about this is that I know those have to exist because we are continuous. So I do need to make the statement that since v at t is differentiable, then v at t is continuous. Okay, so now we've got to say, well, I know -8 is between these values. So, and let's address what values those would have to be. Initially, we are given that the position at 0 is -2. And then we also found that the position at 3 was -10. And so since -8 is between those two, so we could say -2 is less than -8 is less than -10, by the intermediate value theorem, there has to be a value so that, and so we can go ahead and make those statements. And let's see, let's go ahead and finish that one. So IVT by IVT, there must exist a value. And that value would be t, so that v at, or x at t, I guess we should say. So that x at t is going to be, what was the -8? All right, and now let's also look, there's probably another place since we had to find that -9. And so looking at this, we know that x at x at 3 is -10, and we know x at 5, let's go up and see, x at 5, yeah, we know that's going to be a -5 or -7, so we can go ahead and say, well, I know there's got to be a value there, so let's go ahead and write out those. So we also know by all of the same idea that x at 3 was -10, and x at 5, we could see that that value is going to be -7. And then we also see that after x at 5 is -7, and then x at 6 is going to be -9. And so notice there's 3 places so that has to be true. Okay, for part C, on the interval from 2 to 3, is the speed of the particle increasing or decreasing? So for speed to be increasing, we need to be above the x-axis and increasing, or below the x-axis and decreasing. Or if we're slowing down, then we're below the x-axis and increasing, or above and decreasing. So that's kind of confusing, but from 2 to 3, if we look at this portion here from 2 to 3, notice that we are below the x-axis, so I know that v at t is less than 0, and v at t is increasing. So notice if v at t is increasing acceleration, it's going to have a positive sign. However, velocity has a negative sign. So they're working against each other. So it's increasing. So speed of the particle is slowing down. All right, and now for part D, it says during the interval, what time intervals, if any, is the acceleration of the particle negative? Acceleration is going to be negative when velocity is decreasing. So that might be something good for us to put down here to justify. So again, acceleration is negative when velocity is decreasing. Okay, and so we know velocity is decreasing over these intervals. V at t is decreasing over, and the intervals would be from 0 to 1, and we're also from 4 to 6. Okay, our next problem is a calculator problem. We've got a particle moving along a curve. We've got this broken up into its parametrics, and we know that at time t equals 2, the particle is at this position, and we also know these two derivatives. So in part A is the horizontal movement of the particle left or right at time t equals 2, and you need to explain your answer and then find the slope of the path of the particle at time t equals 2. So for the first thing is the horizontal movement of the particle left or right at 2. So let's see, horizontal, that's moving along the x-axis. So we need to find dx dt at time t equals 2. And again, this is a calculator problem. And so, or let's see, I just look at this one, and you're going to end up with square root of 2 over e squared, and 2 over e squared is greater than 0, so the particle is moving to the right. All right, and so let's look at our next problem. We've got to finish this one. Sorry, guys. Now we need to find the slope, and finding the slope, keep in mind that that is dy over dx evaluated at time t equals 2. And so again, you would have sine squared t over all of this, and then plug in a 2, and you should get, it looks like, about 3.055. Right, and so now for part B, the x-coordinate of the particle, find the x-coordinate, the particle's position at time t equals 4. Now, luckily, we were told at time 2 that we're at 1, 5. So if we want to find the x-coordinate at 4, that's talking about the position at 4, is going to be equal to 1 plus, and then if we want to know at 4, we knew or was given 2. So we're going to integrate from 2 to 4 of our x-coordinate. So that's going to be x prime at t dt. And so if you put all of that in the calculator, hopefully you will get about your position x at 4 is going to be 1.253. Okay, in part C, we are going to find the speed of the particle at time t equals 4. And so the speed of the particle, we are going to go through and we're going to have the square root of, and then we've got x prime at 4 squared plus y prime at 4 all squared. And again, once you get that in your calculators, hopefully that's going to give you 0.575. And then it also asks us to find the acceleration vector at the particle at time t equals 4. And so for that one, then we need our second derivative. So for acceleration, I'm just going to separate this. For your acceleration vector, you're going to have, it's the second derivative of your position and comma second derivative of that position. And hopefully with the aid of the calculator, you got 0.041 comma 0.989. Okay, and then lastly, we need to find the distance traveled from 2 to 4. And so if you want to find that distance traveled, your distance, you are going to integrate from 2 to 4. The absolute value of your velocity here, or you can go ahead and do or integrate your speed. Sorry, I was thinking we didn't have parametrics. So you would integrate that speed from 2 to 4. So that's going to be x prime at t squared plus y prime at t all squared. Okay, our next problem, find the speed of the particle at time t equals 3. So finding our speed, again, that's going to be the square root of x prime at 3 squared plus y prime at 3 all squared. And hopefully that's going to get you 2.828 meters per second. Okay, and then part B, the total distance traveled from 0 to 4. So you would integrate your speed essentially from 0 to 4 square root. And for this one, you're just going to have your x prime at t squared plus your y prime at t all squared dt. And that should give you 11.587. Okay, in part C, you want to know when the line tangent to the path of the particle is horizontal, and then you need to know the direction of motion of the particle toward the left or the right and justify your answer. All right, so for that one, first thing we need to realize though is if we're talking about our tangent line here being horizontal, then we definitely need dy dx to be equal to 0. However, dy dt, that's what we need to be 0, and dx dt does not need to be 0 at those times. So looking at that, when that's going to occur, and really you could graph these and see where we cross the x-axis. So it looks like t is going to be 2.2079. And now you can go back and plug that time into your velocity. In other words, find x prime at 2.2079. So go back and substitute that in. And so that's going to be a positive value, so the particle is moving to the right. All right, and so now let's look at part D. And part D has a couple of different parts to this one. It's kind of a strange problem. And so for the first one, it tells you that there's a point with x coordinate 5 through which the particle passes twice. So in part 1, it wants us to find those two values, find out when those occur. So I'm going to say 5 equals, because again I need that position. So 5 is going to be equal to whatever that was, that x. I need to come back up and look. T squared minus 4t plus 8. So t squared minus 4t plus 8. If we solve this, of course you can type it in the calculator, but some of this is just easier to solve by hand here, and that's going to be t minus 4. It's going to be t minus 3. How about that? T minus 3 times t minus 1. So you have 2 times at 3 and at 1. All right, so there's your first part. And then it says the slopes of the lines tangents to the particle's path at that point. So it wants us to go back and find the slope at 1 and our slope at 3. So let's go back and find our slope at time t equals 1. This is for the second one. At time t equals 1, goodness, our dy dx is going to be equal to 0.432. And then at time t equals 3, our dy dx, that is going to be equal to 1. And then, let's see, we need to go find the y-coordinate of that point, given y at 2 is all of that. Now, that weird y at 2, that is so strange, but we can go, that's really your initial value. And it looks like we might have already knew something. All right, so it looks like we might have to go find some values here. Some integration should be involved here, I think. All right, so let's go find some of these values. To find our place at 1, we're going to say our position at 1 is going to be equal to, now we have our position at 2, and this one's a little different here, because this initial condition that we have is at 2, but I want to get back to 1, so really I'm going to have to subtract. I've got to move backwards here. And then that's going to be from 1 to 2 of dy over dt. And hopefully that will generate 4. And then going the other direction to find our position at 3. Now the position at 3 is going to be more of the traditional plus, because you're at 2 trying to get to 3. Up here on this one, I was at 2, but I needed to get back to 1. That's why I was subtracting. And so down here, and oddly enough, if you type both of those in your calculator, you get 4. All right, so for A, if we're going to talk about the line tangent being vertical, so let's think about slope, because again it's talking about a tangent line. And so you are talking about dy over dx, and you're not given dy over dx. You're given dx over dt and dy over dt. So you've got some things you're going to have to address here. First thing is you need to show that dy over dt over dx over dt, that will simplify to be your dy over dx. That is important for us to show, hey, I know that has to happen. And if I'm going to talk about a vertical tangent line, so that means that dy dx, when we talk about that, we're looking at where dx dt is equal to 0. But now we don't want 0 over 0, right? We don't want that to happen, because we know that causes black holes. So we also need this at the same time to happen. Those are the things I need to happen at the same time. So we have a graphing calculator, right? So we need to graph this portion, and we need to see where it is 0 over this time frame. And find those t-values, and then we need to make sure those t-values, if I were to plug those in, that those t-values in y are not 0 at the same time. So let's see if we can find, I think there's about 2, maybe 3 when I work through it. I know for sure 2. Okay, the time values that I got were 1.14473, and I also got t to be equal to 1.25331. Okay, so for part B, you need to write an equation for the line tangent. So if you're writing the equation for the line tangent, you definitely need your formula way back when we said y minus y1 equals m times x minus x1. Hopefully we remember that. We do need to find m. Remember, m is going to be your dy dx. So first thing we need to calculate would be dy dx at time, what was it, 1? At t equals 1. Let's check our answers for our slope. Let's see, I got 0.86344. That was my slope. So I have that portion m, that's going to be that value over there. Now, notice what we were given is velocity vectors. But I need y1 and x1, and those are positions. That's an ordered pair or a point. So what I'm going to have to do is get back to position, and to do that from velocity, we have to integrate, right? Mm-hmm. So I need my position. It wanted the position at 1, wasn't it? So what we'll have to do is look for something we know for sure, which we know for sure at time 0, the position is -2 and 3. So to generate our position at 1, what I did was say, okay, I need my position at 1. That's going to be equal to, well, I know at 0, for the x portion, I'm at -2, right? That's where we're sitting. Plus, and now we're going to generate, this is where we're going to need to do some integration, and we're going to go from our known to what the new would be, from 0 to 1, and that's why we're putting that -2 there, is because I know that 0 value. And then we have our velocity, and that one was, you can put, what was the notation there? dx dt, or even, I even shortened it and did this. If you want to. You don't have to rewrite the whole thing on the calculator portion. You can just note what you're integrating. So that would be for the x position. What about for the y position? We would still do y1, wouldn't we? We want our position at 1.
3 plus the interval 0, 1.
There you go. From 0 to 1 of y prime at t dt. So for x at 1, I got 9.314695. That's ginormous decimal. And for the position y at 1, I got 4.620537. Okay, now check your work, and now we need to put this together in the equation of a line, because again, we've just found the pieces of it. Definitely need to put that together. So we're going to have y minus And I would do 4.621 maybe. If we wanted to round it or truncate, either one, equals our slope, which was 0.8634 times x minus, and then 9.315. For part C, you're asked to find the speed of the particle at 1. And when we do speed of a particle, it reminds me of doing the Pythagorean theorem, really, or the distance formula, because you look at the rate of change of this part here. So you're going to have your x prime at 1, whatever that value is squared, plus your y prime at 1, all squared. And that's coming from, if you want to think about it on the xy axis, dy or dx dt, or even just your x prime, that's talking about your rate of change this direction. And then you've also got your rate of change going this direction. And so you're actually finding that portion there. That's what's going on with it. So again, calculator, this is all the setup you need to show. And then you just go back over and do some number crunching in that calculator. So the speed for this, you should end up with what I got was 4.10526. And of course you can truncate or round throughout there. Okay. Now for acceleration. So again, you've got your velocity. So to get to acceleration, we need a derivative, don't we? And so really the only notation we need to show for this would be, of course, you're in vector notation. So that's why you've got the little bent parentheses looking things. And so you have a derivative already, or since we're looking at that in terms of a position, that x at t, you can say, well, I know that's the second derivative at 1, comma, and then second derivative of y at 1. All right, the values I got there, you should have negative 28.425. Oh, well, it'd help if I wrote a 2 there, then the 5. And then 2.161 for the acceleration.